All right. What's up, guys? Chris the Ninja here, and welcome back to Study Sessions. I'm your host, Chris the Ninja. I said that already, but I like saying it twice. Don't hate on me, but I like saying it twice. All right. I just like it. All right. I'm just making sure I got a good, making sure I got all my stuff out my bag that I need to get out of the bag because got quite a few things I gotta work on this weekend. But one of those things happens to be not really any exams or anything like that right now. Um, I'm actually kind of chilling on exam prep. I know it's kind of a luxury that I did not actually expect to have. Um, but you know, it happens sometimes. So with that luxury of extra time, I decided that I would go back to my roots of study sessions and give y'all. Is this not the? No, this is the one that's. Hold on, there we go. I thought it was not that kind of roots and study sessions and give y'all a study stream based off of what I started study sessions for the first time, and that's ESET 355. So, without further ado, wait, why is this private? Why does it say private? Hold up, I'm not going to let myself be embarrassed like this. Okay. Hey, what's up, Cyan? Welcome to the stream. Thanks for being here. Okay. Further ado, lights off. Let's get started. So, fortunately, study sessions helped me pass ESET 355. It just did. Um, so I'd like to kind of give back to the 355 community, which is high frequency electromagnetic waves and systems. Now, this is going to be like study sessions set freak. Oh, bro, what the study sessions pure review. Now you might be thinking to yourself, like, why, Chris the Ninja, would you put yourself back through this stuff again after escaping it the first time? I say to you, if you were stuck in a pit and someone helped you out, wouldn't you help the next person out of that pit? That's what I'm saying. So the first thing that I'm sure you all, if you are in 355, have gone over is AC concepts. Now, I actually, instead of rewriting all these notes, I'm not rewriting all these notes. I'm just gonna give y'all like the Spark Notes version of it. So AC concepts, we all know capacitor. We all know you have capacitors, inductors, and resistors. You have three main components. So you have a. I haven't written anything yet. So you have capacitors. Jeez, Louise, I need to hold up. I need to like move some stuff around so I can actually make this legible. So if you've been to any of my study sessions before, you know we have capacitors, inductors. Oh, I should probably thicken that up a little. Well, actually, no. Well, should be fine. Inductors and resistors. Each of these components have the other components in them. It's like basically like playing a game of like what do you want more of? And just for visualization, on a circuit board, capacitors look like that, or on a like when you draw a circuit on paper, capacitors look like this, inductors look like this, and resistors look like that. Um, I know it's a slow burn. Trust me, after like 5 more minutes, it's gonna really kick up. So filling up with some candy, getting myself some energy. I'm tired, like real tired. Um, Now zooming in on the capacitor, which is the main part that we're going to really be working with for most of 355, and this is probably like what you'll end up seeing on your 355 exam. Now, what do you notice about capacitors? It has two leads and two metal plates. So you got these leads, but what's something that we all inherently know about how electricity works? We all know V equals IR. Well, when there's a short circuit, that's basically zero resistance, but that would mean there'd be zero voltage, which means there would be zero current or infinite current, but basically still zero because zero times anything is zero. So that means that any wire, such as this lead, has to have some tiny bit of resistance in it. And then that leads us to how a capacitor is actually structured. And then that's where I'm going to come back to the old notes. These are the notes that I took for myself. Looks crazy, I know. But basically, capacitors, they store energy. You have your permittivity constant. Well, inductors store current. How am I going to go over this? Okay, okay, okay. I figured that. On the exam, you will probably be asked something pertaining to epsilon R. Epsilon R is the permittivity relative to a certain material. You'll probably be given that epsilon R, but you need to know that epsilon naught is 8.85 times 10 to the minus 12 farads. That lets you know it works with capacitors, and we're dealing with capacitors for most of the course. Um, so this is just like a circuit example. Um, when the switch is open, V equals 0, I equals 0, and then T equals 0, the switch is closed. So at that time, T equals R times C. Um, what the heck did I write here? I think that's what 1 microsecond. I think that's 1 microsecond. Um, okay. So first math part of the stream, just deciphering this stuff so I can remember it because it's been a while, and it's probably been a while since the beginning of the semester for y'all. So you might have some of this slip. So to find a V, what is that, VC or VT or whatever, you do 1 minus, and then you do E, raise that to the minus 0.000001 over 100. So I think it's 100 ohm. Yeah, 100 ohms times, I think that's 10 nano. I think that's 10 times 10. Yeah, hey, I did it. And that gives you like 0.63. So that's like 0.63 volts, which is what I have here. That's what I have here. Um, that's not really that important, but the important thing to note is that current for a capacitor, first of all, it leads by 90 degrees, and the current for a capacitor is equal to C times the change in voltage over time. So as long as voltage is changing, the current keeps flowing. That's why AC signals work with capacitors, and that's why as the frequency goes up, the um the the resistance of a capacitor, the reactance of a capacitor goes down. If you're changing voltage extremely quickly, like between positive and negative, like even if it's just like like 1 microvolt, changing extremely quickly that way will create an extremely fast current or extremely high current because you'll have like a large number over a short period of time, makes a huge current flow. And that means a lot of current flowing through one spot, making it have less resistance, blah, 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 math, whatever. So that's what I want to put here. Um, an inductor has these mu terms. And it's important to note that mu is never just mu. Mu is never just mu. It always has mu naught times mu r. But most of the time, mu r is 1. And then that leads us to this example. Mu equals 2, n equals 2, a equals 8, l equals 10. That's this equation, mu times n squared times area over L, mu times n squared times area over L. That gives you 6.4 over 10 equals L, or 6.4 henries. Then I just talk about like impedance. And this is something that we'll get into over the summer. This is like this little thing right here is like a little fun project that we're going to get into over the summer. Should be great. Um, but yeah, hopefully y'all understand like the basic stuff um of like capacitors and inductors and stuff like that. So circuit behavior. So when dealing with actual real world components, it's not ideal as the theoretical components. Like theoretically, a capacitor would have zero um, resistance and have zero inductance in it, but that's just not the case. Um, or resistors would have no capacitance, but like this is the actual circuit of a resistor. And the whole point of this class in 355 is learning about how parasitics affect radio frequency or RF. Um, and that's kind of like, that's kind of the point of the class. So the inductance here, shown right here, is because of the leads. Any length of wire is not going to be a perfect length of wire where there's no inductance. It's going to have some type of inductance that comes with it. I'm just going to have some current stored onto it. Um, sometimes the inductance can be neglected, but not at high enough frequencies. Um, this is a this is if two wires are going next to each other. So like two wires, and ideally, two wires are going to look like this. There's going to be two straight lines of metal, but two pieces of metal put close enough in proximity to each other. Just draw my calculator. Two pieces of metal close to each other with a dielectric in between creates a capacitor. Well, that's essentially what we've done here. We have two pieces of metal, so copper, two pieces of copper. The dielectric here is air. So we've essentially made ourselves a broke man's capacitor. And that's what's shown here. That's what this capacitance here is shown. That's what that's shown to be right there. Um, Now, if you want to find the capacitance between wires, which you might have to find this on the third exam, it might be on the final, hint, hint, practice everything, literally practice everything. I haven't been in the class, so I barely know what I'm trying to tell y'all. I'm just trying to give y'all a quick little review and go over some concepts a little bit kind of quickly. Um, if you want to find the capacitance between wires, you just do C equals pi times epsilon times L over the natural log of D over R. Now, what does all that stuff mean? Well, glad you asked. So, as I say here, R is the radius of the wire. This D is the distance. Oh, geez, I need to bring this down like a little bit. D is the distance between the wires. You have L, which is the length of the wires overlap point, like overlap. Because there's times when you'll have a shorter wire than the other, one that's next to it. And what ends up happening is some of that field will radiate out and circle back, but that gets into like real RF stuff, which I'll get into soon. Um, and then epsilon, epsilon of course is epsilon naught times epsilon r, and then you have pi, and pi for anyone who doesn't know is just a number. Pi is just 3.14159. I think it's like 6 or something like that. Something weird, bro. Pi is one of those numbers like you learn about pi and then you kind of forget about pi and then you see pi everywhere. Oh, sorry, I have to blow my nose. I can't breathe. Okay, so so with this right here, let's do an example problem. So find the capacitance between these wires. So this would be a great time if you're watching the video back to pause and make sure you understand the concept of it. So I'm going to come with like some problem and I'm going to do it, but you're going to pause the video if you're watching it back and it's not live. And then you're going to see if you match the answer with my answer. Now, if you have a piece of paper next to you or an iPad or a phone or a calculator or something like that, try to do the problem with me. So we're going to do an example. I like the color blue, so we're going to make the examples in blue. I have two wires and two wires are 3,000 meters long. And they are separated by 80 meters. Now, this is an unrealistic example. Well, I mean, it's kind of realistic. I mean, you might have this might be, well, this is unrealistic for like RF stuff, but like just for sake of argument to have some work with. So you have 80 meters between them. Um, the radius of the wires are like we're working with hey Google, what is the diameter of a 22 gauge wire?
Here is information from Carrera testing.
So we're working with 22 gauge wire for whatever reason. So two 22 gauge wires are 3,000 meters apart and separated by, or 3,000 meters long and separated by 80 meters. Um, let's see. I'm trying to find like a real world kind of example. Did I say it was permittivity or permeability? Yeah, it's permittivity. So permittivity, we'll say the permittivity of this, we're working with like moderate grade aluminum. So like we'll say epsilon R is a the aluminum's like been degraded. And now has a relative permittivity of 4.13. So what's the capacitance between these? I think I gave you all enough information. So what's the capacitance? What is the capacitance of this set of wires? Now would be a great time to pause to see if you understand. If you don't understand, work along this with me. If you do understand, check your answer in about 1 minute. If you're on the stream, take a crack at it. There's an infinite number of wrong answers, but you've been given all the information to know the right answer. So the first thing you're going to do for solving this problem, I'm going to solve the problems in purple so we don't get confused. So we know that C equals pi times epsilon times L over natural log of D over R. Well, now it's just a plug and chug problem. But we need to know what, but we have to remember epsilon is actually epsilon naught times epsilon R. So um so epsilon R we know is 4.13, then that's multiplied by 8.85 times 10 to the minus 12, because that's what epsilon naught is. Now this would be a great time if you're a smart cookie like I was that passed 355, because that class is something else. I'm telling you now. You'll put that in your calculator, so you can just go to like 8.85 times 10 to the negative 12th, and then just store that as, I don't know, maybe E for epsilon. Then you could just do E times 4.13. Wow, now you have a value that you can just like throw into stuff. So that ends up being like our epsilon ends up being about 3.655 times 10 to the minus 11. Um, and then we multiply that. So we do the epsilon times 80 times pi. Because well, no, actually, no, not 80. Times 3,000 times pi. So if I were to multiply this by 3,000, then multiply that by pi, you get 3.44 times 10 to the minus 7th in the numerator. Then that's being divided by the natural log of 80 over 22 gauge wire. So now this is where you would look up what like the width of 22 gauge wire. In millimeters, that is 0.6426 millimeters. Oh my goodness. 0.6426 millimeters. So if we're working in meters, we have to convert that. So the our R value equals 0.6426 millimeters, or 6.426 times 10 to the negative 4th meters. So you do 80 over 6.426 times 10 to the minus 4. Do 80 divided by that natural log of that. That gives us like 11.73 on the bottom. So we end up having 3.44 times 10 to the minus 7 over 11.732 farads. And then if you want the actual answer for that, I got you. Don't worry. You get about 29 nanofarads. So C ends up being like 29 nanofarads. Now, that's not that much. That really is not that much capacitance for like the size of wire that we have. But you got to think about it, right? 29 nanofarads may not be that much at like 50 hertz, 1,000 hertz, 20,000 hertz. But what about like 85 billion hertz, 23 gigahertz? How is that going to affect stuff from here? So you know what? Let's just let's just box that and save that 29 nanofarads for some more of these complex problems that come from this stuff. So that's an example on that stuff. Um, you might be asked what a capacitor equivalent circuit looks like, or you might be asked to draw it on the exam. It's important to know that it looks like this: inductor, resistor, feed, like drain resistor and capacitor. together. And that's how that works right there. Um, you can find the you want to find the resonant frequency of a capacitor. Here's the derivation of that equation. Basically, all you need to know, F equals, goodness, like I see now why Dr. Hudson does not deal with this stuff, man. I hate deriving stuff. It's so tedious. If you want to know the resonant frequency of a capacitor, it'll be on the formula sheet. Don't worry about it. Just put this down. Put that down. That's the resonant frequency equation. 1 over 2 pi square root LC. 1 over 2 pi square root LC. That's all you need to know. Oh, one thing you should know, one thing that's very important to know that a lot of people tend to forget. Trust me. You're going to say to yourself, "Oh, I don't need to remember that." Everybody forgets this at least once. Omega is 2 pi f. I'm telling you, remember this fact. If you're going to be in any type of electrical signal processing, electronics, electrical engineering, whatever you're going to do with, if you're dealing with frequency, omega equals 2 pi f. You will save yourself so many headaches if you drill this into your head now. Remember that equation right now. Remember it. All right. All right. Cool. Let's see. Inductors, impedance is J omega L. Find X, L with omega L, 2 pi FL. Find the reactance, resistance. I mean, if you want to find the resistance, you have omega L equals 1 over omega C. This is like to find the equivalent ones. Find the resonant frequency of a 1.01 microfarad with a 1 nanohenry series of inductance. So this is how you find that. And you get basically frequency 1 over 2 pi square root of LC. So actually, let's do an example of that. Let's do a quick example. Let's just say 29 nanofarads. Huh, crazy. I wonder where we got that number from. Maybe you should rewind the video that you skipped half of because you got tired of hearing me talk about something you weren't necessarily interested in. Crazy. So let's just say we have a 29 nanofarad cap. Also, resistors are not affected by frequency. Their resistance value is not affected by frequency. So we'll just say like this is 1 ohm. Doesn't really matter. 29 nanofarad capacitor. Power source. And let's just say, let's see, what can I say? Let's say it's 76,000 hertz. So find the resonant inductance. Oh, that's a little different, huh? That's a little different than what you was expecting me to say, huh? Thought I was gonna make it easy on you. Nah, I'm not gonna make it easy on you. So we're given this equation right here. F equals 1 over 2 pi times the square root of L times C. Well, we know what F is. We know F is 76,000 hertz. We know F is 76 kilohertz. We know that we know what 2 pi is. It's just 2 times pi. And we know the square root of L. We know what C is. No, C is 29 nanofarads. Right? I think that's the value I found up there. Yeah, that is. So no, C is 29 nanofarads. C is 29 nanofarads. So how do we solve this? Well, we pull out our old friend algebra. Our old friend algebra. Everybody left the stream when I said algebra. So this is just kind of like rearranging equations, simple equations to rearrange, but you're probably gonna have to rearrange something like this for the exam. I can almost guarantee it. Let me just fresh page. Okay, cool. So you're gonna take in order to rearrange this, the easiest way to do this is first to multiply by a square root of LC. Doesn't really matter what LC is, but you multiply by the square root of LC. Then you'll have 76K hertz times square root of LC equals 1 over 2 pi. Now, you might ask, why did I do it that way instead of like trying to get stuff solved and whatnot, blah, blah, blah? It's because I already know what 2 pi is. I don't need to solve for 2 pi. So now all I have to do is divide by 76,000. Square root of LC equals 1 over 2 pi times 76K. That's just how it works. Because it'll go in the bottom of the equation. Then you got to square it. Get rid of that square root. So LC equals 1 over 2 pi times 76 kilohertz squared. And then divide by L, or divide by the 29 nanofarads. So L equals 1 over 2 pi times 76 kilohertz squared divided by 29 nanofarads. So to find that resonant inductance at this frequency, now it's a calculator problem. So we want to find L. You want to find L, so we do 2 pi. Wait, 2 pi. No, hold up. Shoot. 2 pi times 76,000. One over that squared. And then divide that by 29 times 10 to the negative ninth. And that gives us an L value of 0.151 millihenry. Now, that's a pretty big inductor if you ask me. Because I don't know if you know about inductors, but inductors, they get really big really fast. A 1 millihenry inductor is like this big. This is a pretty big inductor for that small of a capacitor. 355. This 355 stuff. I'm just going over it just in case, people want to review that. Or in case you're, interested in electrical, ESET, something like that, where you're going to have to work with frequencies. or capacitors or inductors. You know, I did this class last year. Um, oh, that reminds me. This this will definitely be on the exam. Propagating waves. ESCT, Electronic Systems Engineering Technology. I'll put it in the chat. Hold up. This I can guarantee you will be on this propagating waves and transmission. I can guarantee you will be on the exam. I can guarantee you this will be on the exam. I bet money on it because I'd make money on it, you know? Um, so propagating waves, what can I say about propagating waves? Propagating waves, they have like this weird thing. You have your time variation. It's all good. You have your time variation and you have your space variation. Um, this is typically in radians per second. This in radians per meter. They cancel each other out, but beta is a phase constant, and that's 2 pi over lambda. That's something you're going to want to drill into your head as well. Beta is 2 pi over lambda, because when you get to Smith charts, when you get to the Smith chart part of the exam, and it's like, find the beta constant of blah, 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 you're going to be there spacing out because you forgot. What did I have this lambda? It's 3.81 lambda and it's multiplied by beta. What do I do? Nothing. The lambda's canceled. 2 pi times 3.381. That's your answer. The lambda's canceled. Something I wish that somebody had told me when I took the class. Something I had to struggle and find out on the third exam. Am I salty? No, actually, I'm not. I'm really not. Boss Hart is one of the most fairest professors ever. Um, I'm going to come back to this when I talk about fourth dimensional numbers. Oh, buddy. When I talk about fourth dimensional numbers, it's gonna be a day. Uh, so let's see. Omega minus beta times dx dt is 0. Um, oh, yeah. So this is one of those equations that like you'll know it and it'll kind of be on the formula sheet, but you're not going to really know it's on the formula sheet. So you might be asked a question about like how velocity relates to omega and beta, and this is kind of how it relates. So I know we're kind of like bouncing around, but this is just like kind of hitting review points that I wish I had known for the exam. Um, so to kind of redo this in a way, so that way like y'all can actually see what I'm talking about. Velocity equals omega over beta. How is that so? Because velocity is also derivative of position, which is also the integral of acceleration. So it's the where the okay, there we go. Please. Thank you. So how in the heck do you get this equation? These are nothing alike, except they are. Because if you look at what wavelength is, omega is 2 pi times f. Beta is 2 pi divided by lambda. Now, what do you know about basic algebra? You know, my shout out to what was her name? I think it was Miss Morgan. Shout out to Miss Morgan, sixth grade math teacher. No, that was my ninth grade history teacher. Uh, Shout out to my sixth grade math teacher though. She was really cool. I think it was Miss Taylor. Yeah, I think it was Miss Taylor. Shout out to both of them. First of all, shout out to both of those teachers. They were great. But anyway, Miss Taylor, we're going to call her Miss Taylor for sake of argument, had this brilliant way of helping us remember how to do reciprocals. You did the KISS method. Keep it, switch, switch. So with the KISS method here, we keep the top and then we switch the bottom pretty much. And then that gives us freaking, there we go. That gives us 2 pi times f times lambda all over 2 pi. Well, now that you see this, the 2 pi's cancel, and you're left with, bro, I swear I hate OneNote sometimes. OneNote is so frustrating at times. Now you're just left with f times lambda. Well, that's what we have here. F times lambda also equals velocity. I forgot why F times lambda equals velocity, but it kind of like, okay, F times lambda equals velocity. It doesn't really matter what lambda really is. Like, it's not all that important. F times lambda equals velocity because of this. Lambda equals velocity over frequency. That's just roll with it. Just roll with it. So so when the propagation effects become significant, when the circuit dimensions are greater than lambda over 10. So you can also find velocity with 1 over square root of mu times epsilon. How in the heck did I get away with that? That is not an E at all. That's not even an epsilon. Golly, man, I was speed writing. And remember, mu and epsilon, they always break down into two different parts. Mu naught, epsilon, mu r and mu r and mu naught, and epsilon r and epsilon naught. Um, so like around the speed of light, that's like if you were to just use like one for everything pretty much and just use like the basic, you basically get the speed of light for velocity. That's how we can prove that velocity is the same. Um, yeah, that's how we can prove it's the same. So velocity also can equal the velocity of the propagation. I should very much change this. So V prop is C over mu r times epsilon r. But if you remember from earlier, mu r is typically 1. See, this is why you don't skip stuff. This is why you start at the very beginning. Because if I had just jumped right into this from the first second I started the stream, and I was like, oh yeah, mu r equals this, somebody would be asking themselves, well, why does mu r disappear? I don't remember why mu r disappeared. Because it equals 1. mu r equals 1. That's why it disappears. Um, so you can find the v you can find v prop. Okay, cool. I don't know if this pen is going to want to work today. We're going to hope so. V prop equals the speed of light. So this is c equals the speed of light. So we're doing c over epsilon r over the square root of epsilon r. That equals v prop. So let's do an example. I love me some examples. I love examples. So example. Oh, let me go ahead and zoom in a little bit. Example. I am really zoomed out. Okay. Find v prop if epsilon r equals 2.41. Find v prop if epsilon r equals 2.41. This might be a short answer question because it doesn't take much effort to answer this question right now. All right. Plug it in your calculator, we'll get the answer right. So we just roll over here. We just put in v prop equals c over the square root of epsilon r. This is also one of the things you should put in your calculator. So 3 times 10 to the eighth, and then you just store that as c. Now you have speed of light stored in your calculator. I'm giving y'all cheat codes, bro. I'm basically giving y'all cheat codes. If you're not using this on the exam, you're wasting time. Take the first 3 seconds, take like the 15 seconds now, and save yourself 3 seconds on the exam. Or reverse that. Take the 3 seconds now and save yourself the 15 seconds on the exam. They might come in handy. Also, when you're doing your equations, it looks nicer. So you can do like now you literally have 4.1. C over 2.41. And that gives you a V prop of 1.24 times 10 to the eighth meters per second. Um, so knowing this, you can find the wavelength. So let's find a wavelength. Lambda and lambda at 40 kilohertz. So we know lambda equals velocity over frequency. So if we know that we have, if we know that we have 40 kilohertz is our frequency, and velocity of propagation is 1.24 times 10 to the eighth, you just divide that by 40,000. And our wavelength is 3.112 meters, or 3,112 meters between each wavelength. That's the wavelength. This is why it typically ends up being in the order of megahertz, because it makes stuff a lot smaller. Actually, I should put that in megahertz. So not 40 kilohertz. Scrap that. We're gonna say 255 megahertz. Actually, you know what? Screw it. We're gonna say 355 megahertz in honor of the class. That gives us a wavelength of Hold on, I gotta double check this. Uh, that's 3 meters. Point 0.35 meters. 0.35 meters. I'm trying to think. I'm overthinking this, by the way. This is 0.3507 meters. $35.07 centimeters. I was overthinking that so much. Overthought that way too much. Way too much overthinking happening right there. My brain's tired. It is what it is. My brain's tired. Let me just double check. 35. Yeah, there we go. Okay, cool. I got it right. Did I say 100? Did I say 100 centimeters? Oh, that's just 1 meter long. That's what threw me off. Uh, all right, cool, cool. Um, the last thing I'm gonna hit on tonight. Let's see, you'll probably have a bounce diagram on the exam as well. So I'm not really gonna write too much about this. This is just like kind of like a reviewing thing. I might write something on it. I don't know yet, but just to review, and then I'm gonna end the study, end the study session. Um, you're trying the whole goal of like learning all that stuff about propagation and stuff like that is to eliminate reflections. So first of all, you need to know how fast the wave is going to know how soon is going to reach the other side of a transmission line or something like that. You got to know this stuff so you can account for it in your bounce diagram. All of it comes back. So I'm going to assume you did well with transmission lines and whatnot. We're just going to go right over here to your gamma values. Resistor here is 30. The resistance of the transmission line is 50 ohms. To get that gamma 1 value, which is the amount of the signal that's being reflected back to you, you do input resistance multiplied by the resistance of the line divided by the resistance added to the resistance of the line. Um, I forgot how far apart these were, but it's something where it's like a few microseconds. You can find that with dividing the velocity that the velocity of the line going across by the distance. They'll give you your time. Um, you know what? I'll come to the rest of this. I'll come to the rest of this next time. I'll do another one. Don't worry about it. We'll get to the transmission lines and like bounce diagrams, but practice your bounce diagrams. Practice those bounce diagrams. It might be on this one. Transmission lines, yeah, right here. Practice this stuff right here. This will be on the exam. I already know. I can tell you it will be on the exam. Might not be a long answer question, but this will be on the exam. And we'll cover this in the next study session. Hopefully, my grandfather will have the time to join in next time, so like I'll actually be teaching him, and I'll actually have something he'll be able to ask me about. So I can actually teach something rather than just like scramble through reviews. But yeah, it was kind of fun coming back to 355. I kind of took me a second to kind of like relearn how to do this stuff. I forgot a little bit of it. I'm gonna be honest, but I hope this will help you. I hope you take my advice about the calculator and some of the stuff you should be studying because I know that exam is coming up fast and you don't want to be left behind. With that being said, I want to say thank you guys so much for watching this video in the stream. If you liked it, strike that like button like a ninja really would. And I'll see all you guys. Oh, subscribe to join the Shinobi. I keep saying it. I forget. I keep forgetting to say subscribe. Subscribe today to join the Shinobi. And I'll see all you guys in the next one. I'm gonna actually like hop on another stream in like 15 minutes, by the way. So yeah. I'll see y'all next time. All right.